But now comes a very interesting point. That is, the acid has been eliminated, but the anion, the conjugate base that's formed, determines the pH of the solution of the equation. What we're left with is CH3COO- reacting with water to form a hydroxide anion, that's what creates the base, plus the weak acid, acetic acid. But we need to be quantitative. How do we calculate the pH of such a mixture? And here's where the equilibrium represented by the weak acid complicates the calculation. In order to calculate the pH, we have to solve quantitatively for the H3O+ in this mixture of a strong base and a weak acid. And so we turn to that problem next. So before we analyze this pH to calculate it directly, let's take a look at the possible circumstances facing a weak acid in aqueous solution. Because we want to stand back whenever we're working a weak acid problem to analyze the possibilities confronting that weak acid. So we know that we can simply add a weak acid to pure water. This is a very simple general reaction where we have the acid added to water that comes into equilibrium with the anion of that weak acid and the H3O+ that contributes the acidity to the water. And just to pin this back to our favorite acid, CH3COOH, when we react that with water, we form in an equilibrium the anion, the acetate anion, and the other component, which is the acidic component, resulting from the extraction of that hydrogen atom from the acetic acid, producing the anion. Okay, now we also know that we can add a strong base to a weak acid. We've already begun to analyze that. And the OH from the strong base will take out every H3O+ produced from the subsequent dissociation of the acid. So this leaves the conjugate base, and that's the acetate anion in our case, that's CH3COO, with a small concentration of OH- and the original acid, which was our acetic acid. In other words, we've reacted the acid CH3COOH with OH- to produce the anion, the acetate anion, plus water. So now the first thing we have to do is we have to calculate the equilibrium constant, and as we reviewed just a moment ago, that's the acid dissociation constant times the inverse of the dissociation of water. That's the acetate anion divided by the product of the concentration of the acid times OH-. So the acid dissociation constant, or equilibrium constant, divided by the autoionization equilibrium for water gives us an equilibrium constant for that reaction of nearly 2 times 10 to the 9. Now the instant we see 2 times 10 to the 9, we recognize that this reaction has gone almost entirely to completion. It vastly favors the product, the acetate anion, over the acid, the acetic acid. So the final point is that we could add a salt containing the conjugate base, that is our acetate anion, leaving a significant concentration of the acid and the anion, the acetate anion, from the dissociation of salt. They're fundamentally the same, and we want to track this similarity between the addition of a base and the addition of the conjugate base directly from some other source. It's a very important unifying idea.